While SpaceX was cranking out a brand new methane Raptor engine almost every single day, NASA and its legacy partners were burning through $93 billion on a rocket that flies maybe once every few years and still costs about $4.1 billion per launch. While SpaceX was literally printing rocket engines out of metal powder, Boeing was taking $5 billion of your money to build a capsule that couldn't safely get astronauts to the ISS on time. And in the background, Blue Origin was talking about the future with BE-4, but was still trying to build engines the old-fashioned way. Most people have no idea what the real difference is. They think it's about Elon tweets, PR, or personality. The truth is much simpler and way more brutal. SpaceX quietly found a manufacturing breakthrough for the Raptor that the rest of the industry either ignored or simply couldn't copy. And that one decision, buried deep in the factory floor, is now exposing who was serious about winning and who was just good at cashing checks. How much do you think they wasted before they realized the game had changed? Because here's what really happened. SpaceX looked at the Raptor engine and refused to accept normal as good enough, immediately rejecting the decades-old approach of legacy aerospace. Instead of designing it like a traditional rocket engine, thousands of machined parts, endless welds, and huge assembly teams, they went all in on advanced metal additive manufacturing. This wasn't just a simple 3D printed bracket for a press release. They rebuilt the entire engine around 3D metal printing from the ground up. Components that used to be separate pieces, bolted or welded together, became single printed structures. Turbopump housings that would have required complex machining and multiple joins were printed as one monolithic piece. Injector plates that normally involve hundreds of drilled holes and handwork were printed with internal geometry no drill could ever make, dropping the part count by almost 30%. That is an insane leap in rocket terms. At the same time, they leaned on laser powder bed fusion, real high-end metal 3D printing, to create curved, branching, perfectly shaped coolant paths right into the metal of the engine walls. This meant better cooling, less weight, fewer joints, and fewer leaks, because every weld seam you remove is one less thing that can crack, leak, or explode, and every braze joint you eliminate is one less point of failure. Raptor's printed parts wiped out huge numbers of welds and joints, which sounds boring on paper, but in reality it means the difference between test, explode, rebuild, and test, refine, scale. Now pause that picture of innovation and look at the other side. While SpaceX was doing topology optimization and AI-driven generative design to decide exactly how much metal to use and where, the legacy system was still cranking through meeting after meeting, requirement after requirement, and committee after committee. Congress was shoveling money into SLS, NASA was writing more documentation, and Boeing was holding design reviews on a capsule that would later be discovered to have hundreds of software issues. And Blue Origin, the company that was supposed to be the other big private competitor, was still building BE-4 with far more traditional manufacturing, more separate parts, more welds, and a slower output. If just one powerful decision maker had looked at what SpaceX was doing with additive manufacturing and said, "We need to switch now," the gap might have been smaller, but they didn't. They stuck to the comfortable methods, proving that institutional failure is often rooted in refusing to change. And the numbers tell you exactly how that choice played out. Because this isn't just a clever engineering story, this is about time and money. SpaceX's additive manufacturing approach cut machining hours for Raptor by around 45%, nearly half the time just vanished. Assembly got simpler, as fewer parts meant fewer steps, fewer tools, and fewer chances to screw up, translating into about a 20% cost reduction per engine. But the real killer wasn't the cost per engine, it was the production rate. Because once you design an engine around printing instead of machining, you can line up printers, you can automate, and you can parallelize, pushing Raptor production to a point where they could make about one engine per day. Think about what that means. Starship doesn't just need one engine, it needs dozens, with a single booster alone using 33 Raptors, which would take years to build with slow, traditional methods. With a printed engine pipeline, SpaceX can feed an entire fleet, achieving a manufacturing velocity the old guard simply cannot match. While SpaceX was doing that, how many BE-4s was Blue Origin finishing? How many SLS core stages were rolling out of the factory? Reality doesn't care about PowerPoint slides. It cares about which company can build a mass-produced engine fleet. You can see the same pattern in the rest of the space industry. NASA's SLS, built with legacy methods and legacy contractors, sits at about $4.1 billion per launch, while SpaceX's Starship, built around mass-produced Raptors and giant stainless tanks, targets something on the order of $10 million per flight. Even if Starship misses that target by a factor of 10, the gap is still humiliating. Boeing took $5 billion for Starliner and struggled for years to get a single clean crewed flight off the pad, while SpaceX took about $3.1 billion for Crew Dragon and delivered more than 40 crewed missions and cargo flights. Shuttle needed months of turnaround for every mission. Falcon 9 can launch again in days. It's the same story again and again. Old system wastes, new system delivers. Here's where it almost got caught earlier. After the shuttle disasters, engineers begged for a new way of working. Less bureaucracy, more testing, more hardware iteration. But instead of fully embracing that lesson, the system patched itself up and kept the same basic cost-plus mindset. If just one reform had really stuck, SLS and Starliner might have looked very different. They were seconds away from learning the lesson that SpaceX later proved with hardware. Meanwhile, in Texas, Raptor engines were exploding on the test stand. Yes, but every failure fed back into faster design changes, new print runs, and new topology optimizations. SpaceX could blow up a Raptor, fix the weak point in CAD, rerun the AI and FEA, send the updated design to the printer, and have a new version on the stand in days or weeks. Try doing that when your engine is mostly machined, hand-welded, and assembled through a maze of suppliers and paperwork. That's why BE-4 dragged on and why New Glenn slipped year after year. If your engine production is slow and rigid, your rocket schedule is slow and rigid. But if your engine production is fast and flexible, you can fail forward at insane speed. SpaceX saw this coming, with Musk himself saying the hard part is not designing a single rocket, it's building the factory that builds the rocket. Everybody laughed. The old guard waved it away, thinking they knew how it worked because they had been building rocket engines for decades. Wait until you hear who knew they were wrong. Because inside the industry, a lot of engineers absolutely understood what additive manufacturing was doing for SpaceX, seeing the part consolidation and the welds disappearing and knowing what one engine per day really meant for production cadence. But the decision makers above them were tied to contracts, lobbying, and political promises. They were locked into factories that couldn't pivot and had careers built on doing things the old way. Admitting that SpaceX's printed Raptor had leaped ahead would mean admitting that entire programs, SLS, certain engine lines, even parts of Starliner and legacy boosters, were dinosaurs. So instead of ripping up the process, they tried to tweak the edges, adjust schedules, ask for more money, and blame COVID or suppliers, anything except facing the fact that their competitor had built a completely different kind of machine. Then reality stepped in. Starship stacked on the pad with 33 Raptors, then flew again and again, not perfectly, but enough to prove the pipeline works, with engines lost, engines replaced, and new designs printed. Each test showed what a mass-produced, printed engine fleet really looks like. At the same time, SLS burned through its first launch at $4.1 billion a shot, with no real path to becoming cheaper. While SpaceX was firing Raptors in rapid succession, Boeing was sitting in front of Congress explaining why its $5 billion capsule still had serious issues after years of delays. While Falcon 9 and Falcon Heavy were racking up missions, Starliner was still working through anomalies. One company was showing what a printed, AI-optimized engine ecosystem looks like. The other was still trying to make the old way good enough. But that's not even the worst part, because at the exact moment the US government was pouring $93 billion into SLS and billions more into slow, fragile programs, China was watching, learning, copying with Long March rockets, lunar plans, and crewed missions all moving forward, aiming at the 2030s. Here's the brutal truth. Every dollar wasted on slow legacy rockets is a dollar not spent making sure we stay ahead. While NASA and Boeing were patching Starliner and rolling out SLS once in a blue moon, SpaceX was dragging launch costs down and cadence up, but the dead weight of old programs still eats budget and time. For decades, old space operated like cost didn't matter, spending like there was no tomorrow on fixed infrastructure, slow production, and rockets that get thrown away every flight. The entire machine was built on the idea that high cost was normal. Then SpaceX arrived with a completely different plan. Make rockets like factories make cars, with engines rolling off the line every single day, production that scales, and reuse that compound savings. Suddenly, the truth was impossible to hide. The legacy system ignored early warnings that their cost per kg was unsustainable. Auditors flagged expenses no one could justify, and they were seconds away from admitting their model couldn't compete. If one person inside the old system had listened, if one decision maker had the courage to change, this collapse could have been avoided. But each warning was overruled, each fix was shoved aside, and each whistleblower was ignored. Buried inside internal cost reports that circulated in quiet hallways and private briefings, was a terrifying line. If SpaceX hits 10-20 kilodollars with full reusability, we cannot compete. This wasn't a maybe, it was a confession. The failure wasn't the high cost, the failure was pretending it could continue. Meanwhile, SpaceX built toward what insiders called the $2 million launch target, a number so low the old system had to pretend it was impossible, but reality only rewards good engineering. While SpaceX was building the most advanced methane engine on Earth for roughly the price of a mid-range house, the old guard was still lighting money on fire, tens of millions of dollars for every single engine they touched, with the RS-25 costing enough that a single unit could buy an entire fleet of Raptors. They ignored the early warnings, the prototype breakthroughs, and the manufacturing experiments that showed what was possible, and the system kept burning money. The moment the Raptor hit that $250,000 target, everything changed, making the tens of millions spent on legacy engines versus $250,000 per Raptor impossible to ignore. Engines per year versus engines per day. The system cracked and you could feel the panic rising, because once you reveal that an engine can be built cheaply, every expensive engine becomes a symbol of failure. Engineers, real engineers, not administrators, knew this years earlier, warning that traditional methods were inefficient and that without major redesigns, cost would remain astronomical. But those warnings were ignored. They sat on desks, buried under paperwork, passed over for safer decisions because a redesign was risky, automation was unfamiliar, and additive manufacturing felt unproven. So the system chose the slow path, the path that cost tens of millions per engine, while SpaceX solved every problem they refused to face. The turning point came when SpaceX reached a production rate of roughly 1 Raptor per day, while the old guard could barely manage hand-built engines in small batches, exposing the brutal truth that the system was broken. Instead of admitting the hard truth, the old system tried to protect itself, insisting the expensive engines were better and that cost didn't matter. But every time SpaceX released new production photos, another simplification step, or another automated tool, the excuses cracked further. The Raptor was a weapon against cost itself, the key to flying Starship often, cheaply, and without asking permission, proving that cost efficiency is the foundation of the entire program. And without cheap engines, low-cost access and frequent reusability don't work. The stakes escalated fast. Early Raptors may have cost millions, but SpaceX treated cost as an engineering problem, not a fixed law of nature. And once they solved that problem, everything around them looked outdated, stagnant, and corrupt. Engines costing tens of millions suddenly looked absurd. Programs built on slow production looked ancient. Bureaucratic excuses collapsed under the weight of a $250,000 reality. SpaceX proved them wrong, and they proved it with numbers. At this point, the consequences were unavoidable. Once you demonstrate that a high-performance rocket engine can be mass-produced cheaply, every legacy program becomes a case study in failure. Every delay becomes embarrassing. Every excuse becomes transparent. Cost difference becomes performance difference. Performance difference becomes mission difference. Mission difference becomes strategic difference. And then the jackpot cluster hits. Bang! The Raptor cost reveals everything that was wrong with legacy engines costing tens of millions. Bang! The production rate of one engine per day exposes how slow the old system really was. Bang! The reliance on manual, expensive methods collapses under the pressure of SpaceX automation. Bang! The entire economic model of traditional engines fails the moment Raptor hits full mass production. SpaceX didn't just beat them. SpaceX obliterated the economic model of old space, making programs that once looked untouchable suddenly look outdated. Launch providers once seen as stable suddenly look inefficient, and systems once praised as cutting edge suddenly look like fossils. Because the moment Starship achieved anywhere near 10-20 Tower kilos, the gap wasn't just wide, it became unbridgeable. Now look closer at the competitive failure. While Blue Origin was struggling to assemble one BE-4 engine every week or two, NASA was bleeding billions on SLS like an open wound, showing how old space culture still destroys American progress. The BE-4's turbopump bottleneck collapsed the entire factory, triggering cascading delays and exposing the truth that the entire crisis started with one specific failure point Blue Origin could never escape. While SpaceX was scaling production like a Silicon Valley hardware factory, Blue Origin was stuck in a cycle of test failure, tear down, inspection, rebuild, retest, wasting 6 to 10 weeks every time a turbopump hiccuped. The public was told everything was fine, but Blue Origin's BE-4 program suffered repeated turbopump and oxidizer turbopump failures during acceptance tests, the critical phase that proves an engine is ready for flight. Engineers knew this would fail at a cultural level, seeing the long hours, the broken safety rules, the rushed procedures, and the fear of speaking up, and they tried to raise the alarm, with one of them losing his job for it. That is your smoking gun. Blue Origin's story, as revealed by its own whistleblowers, is the opposite of success. Reality shows a crack, the messenger reports it, and the system punishes the messenger, ensuring the crack will grow. And SpaceX saw this coming. Elon Musk himself warned about methane turbopump challenges years before Blue Origin revealed their problems, calling large methane turbopumps one of the hardest engineering problems in rockets. Meanwhile, Blue Origin pushed BE-4 propaganda while hiding just how bad the failures were. Insiders and contractors flagged turbopump delays in 2018, warning about slipping test results and documenting oxidizer pump anomalies. But official timelines kept promising the engine was coming soon. Then one acceptance test came seconds from catastrophic failure. Pressure spiked in the turbopump. Data showed a resonance mode forming, and if the operator hadn't aborted, the engine would have self-destructed, setting the program back another year. Slower monthly production meant more labor hours, more manual steps, more rework, more inspection, and dramatically higher costs, while SpaceX's automated processes slashed labor overhead while increasing consistency. While legacy builders crawled along with high-cost, low-volume production, SpaceX turned daily builds into a scalpel, cutting waste, cutting delay, cutting unpredictability. Meanwhile, SpaceX's reusability program provided hard flight data, proving real durability, something slow programs never had. Here's the devastating revelation. High-rate production with automation and AI-driven QA actually produces more reliable engines than slow, handcrafted processes. That's not opinion, that's what statistical models confirm. While SpaceX was building engines daily, learning daily, improving daily, the slow programs were stuck in a loop where the next chance to learn came only once a month. Imagine trying to improve your skill at anything if you could only practice 12 times a year. The lesson is brutal, simple, and inescapable. In aerospace, reality rewards speed of learning, not speed of excuses. The old system built one engine a month and called it care. SpaceX built one engine a day and called it progress. And progress won. Traditional aerospace believed slow meant safe, but slow meant blind. Slow meant delayed fixes. Slow meant repeating flaws instead of eliminating them. And slow meant being left behind. Blue Origin tried to bury the fact that BE-4 engines routinely failed acceptance tests, tried to hide turbopump anomalies, and delayed public updates for months at a time to avoid facing investors, contractors, and the DoD with the truth. Vulcan couldn't fly because BE-4 was broken, but they never framed it that directly. The ultimate consequence: United Launch Alliance, once America's premier military launcher, nearly lost national security contracts because BE-4 delays stalled their Vulcan rocket. With every month BE-4 slipped, the US military's new launch strategy slipped with it. Meanwhile, China accelerated Long March 9th development, aiming for 2030 lunar flights, while the US fights engine bottlenecks from a private company that was supposed to be the SpaceX killer. Even today, BE-4 output is painfully slow, roughly one engine every week or two, while SpaceX has days where they produce 2 Raptors before dinner, and the turbopump bottleneck is still the choke point. So what's the lesson? When you base your engineering on reality, not politics, you win. When you design for reuse instead of retirement, you win. When you build engines at 1 per day instead of 1 per quarter, you win. That's why SpaceX's cost numbers hit so hard. 60-70 kilos today, 100 kilograms depending on payload, and a roadmap pointing to 10-20 kilograms once full reusability locks in. The only real punishment came from reality and from competition, because while they wasted billions, SpaceX quietly proved their model, with their factory acting as a weapon. But here's the unresolved truth you need to hear. The old system still exists, the waste still continues, and your money still funds it. They haven't learned the lesson, they haven't fixed the problem, they haven't admitted the failure. The people who made the worst calls mostly kept their careers. The companies that delivered late and over budget still get contracts. And the next program they roll out, it's already showing the same signs: high cost, slow production, and zero scalability. The same system that created SLS-level waste is now starting new programs, writing new contracts, and promising that this time will be different. China is still racing for the moon. Legacy contractors are still lobbying. Slow programs are still eating budget that could be building the next wave of Starship-class vehicles. Reality cares about who cuts part count, who kills welds, who optimizes topology, and who prints metal instead of stamping forms. SpaceX chose to learn. The others chose to delay, and your taxes are still paying for the delay.